Hi, everybody. So thanks for having me, Clojure Tray. This is my first Clojure-related talk, so I hope you enjoy it. So a bit of background about myself. So I'm a software engineer at Funding Circle. So Funding Circle is a fintech in the UK and US, and fast-growing, and we are hiring. So if you're looking for a Clojure job, just come and talk to me after my talk. So the title is DDD, so domain-driven design in a Clojure event-driven application. So quick show of hands, who knows about domain-driven design? Oh, quite a few. So another show of hands, who uses domain-driven design on a day-to-day basis? Yeah, a bit less. All right, so let me give a bit of background here. So we have been a kind of fast-growing company over the last few years, and this is the same old story. We start with a monolithic application that does the job, and then it grows over and over, and then we end up like with a few bugs, not so great models, and it's difficult to scale also team-wise because we have so many engineers now. And so we set out to do that transformation project of converting that Ruby application into a brand new microservices-based, event-driven, insert the new buzzword here, platform using great technology. In our case, that's Clojure and Kafka. So a lot of materials exist on how to kind of design monolithic application, but there is quite less guidance on how to design microservices, and even less for event-driven applications. So my question is, how do we create a well-thought-out, effective, and extensible design? And so for me, it's kind of similar to how you want to learn how to draw properly. So to draw properly, you actually need to learn and acquire skills using different techniques. You need to get a sense of proportions, know how to represent depth into a scene, how to create the impression of shadows, because of the light can be different also in the scene. And so to that, you will use tools like different pencils. Some are soft and some are hard. And also a good eraser, okay? Don't forget the eraser. So enters domain-driven design. Domain-driven design is a set of tools to help design and implement complex software. Actually, that's the name in the introduction. This is what told to us. There is actually two books that makes reference here. So the first one is the Blue Book, written by Eric Evans back in 2003. And it's kind of hard to read, 400 pages. There is another one, which is more recent, written by Von Vernen. And that one is domain-driven design, implementing domain-driven design. But it's over 600 pages, and it's also very hard to read. So I guess design is hard, right? So fortunately, there is an abridged version of the latter, and it's called Domain-Driven Design Distilled. So what DDD brings us actually is mainly patterns, and there are two levels of patterns in DDD. The first one is strategic, and it allows you to deal with large models. It will help you divide the work that you are going to have to do on some problem space across teams, and help you deal with a way to integrate that work, okay? And the other one is the tactical level, which is more focused around the code, how you manage the complexity of that code, and make sure you have clarity and behavior within the domain itself. So the first strategic important that I want to introduce is bounded context. So bounded context, it's just a part of the problem space. So the things which are inside one context might have a different definition inside another context. So try to think about a customer, for example, at Amazon. So when you reach the landing page, you're going to browse a little bit. You're trying to maybe make a search, and you will get results. And Amazon doesn't think about you like, oh, this is this customer has this address, etc. That will probably come after when you are at the checkout level. And first, it's more like what you like, what you have bought before, and so we can like maybe have some recommendations for you. And that means, like for example, at Amazon, you will have this like search or browsing bounded context, and then later on the checkout or basket, if you want context. Okay. So still a bit abstract, right? So let me give you an example. So I'm sorry it's a bit blurred. So it's not because I'm crappy at taking snapshots. It's because it was required from me to not show the details of our architecture. But actually, you don't need to have those details, because I will just explain very broadly how it works. So this is how our architecture looks like. So we have those different domains, so bounded context. One is repayment processing. The other one is loan servicing. We have distribution, and we have money movements. And the last one is investor. So I didn't mention it, but Funding Circle is a marketplace lending company. So what we do is we connect borrowers and investors using our marketplace, and we try to make a good deal for both the borrower who make a loan and the investors who lend the money, and which allows the borrower to take that loan, right? So these contexts, they are small and they are focused. So they do one thing and they try to do that thing particularly well, right? They are loosely coupled, so they don't have like tons of interaction with each other. And we'll see in a short while how they communicate. To give you a sense of the size, the loan servicing, which is the one on which I've been working, is approximately 1,600 lines of Clojure code for the production code. And there is more actually testing code than production code. And out of those 1,600 lines of code, there is 1,000 approximately which deals only with business logic. So within each bounded context, we're going to have specific words to talk about the things that we are dealing with inside that context. And for example, the data flows like this. So a loan application comes in, and then there is a loan, and we're dealing with the repayments. And the repayments get into the loan servicing. We track the balance of the loan, and then we distribute the money to the investors. And in the investor bounded context, it's all about reporting, making sure that the investor have the right amount of return on the money they invested. So in order to define that language, those words, there is a pattern in DDD which is called Ubiquitous Language. So it boils down to the question of which are the words that we are going to use to reason about the business from a programmer perspective. So for example, are we going to talk about repayment or just payments? Will it be reversal or chargebacks? Will it be balance, loan balance, or outstanding? Those kind of questions. And there is a very good way to answer this question is to have an event storming session. And this session is actually, the goal is to bring the developers and the domain experts together and try to build a shared understanding of what can happen at that point in time, what should never happen, what are the names and what are the verbs that we deal with. Yeah, so the outcome for us was this, this big fresque of all the events, and the blue lines are the boundaries of the context. So for example, we learned that loans are not created. This is not the word that the business uses. They say originate, so loan originated. The loans are delinquent, they are not late if a borrower doesn't pay at the correct time. The repayments, they are authorized and then released from a business perspective, right? That kind of precisions, which were super useful. The benefit for the developers is a very good understanding of the whole business, just not their little island on which they're working, but the whole thing. And the immediate also benefits is that these terms, they end up in the code, so you don't have a different representation between what how the business think about the thing they are dealing with every day and what the developer think of it. So now, how do we bind this context that I showed you before together and make them communicate? So this is what context mapping is about. So it's about choosing the mechanism that will help you bind those contexts technically, but also help the teams work around this context, okay? And you can combine them. So this is the list of the mechanism that I have available to connect those bounded contexts. And we're going to look at the circle one, okay? Just don't do a big ball of mud, please. All right. So the first mechanism is customer-supplier and anti-correlation layer. So I'm going to talk about those two. So consumer-supplier, it's the most prevalent relationship between the context in our system. So there is an upstream supplier, and there is a downstream customer. Very simple. And this is super easy to do with Kafka and Kafka Streams. It's just data flowing through, ready? There is no IPL call. And this ACL that you see actually stands for anti-corruption layer. So anti-corruption layer is making sure that things that do not speak the language, the ubiquitous language, don't end up in your system like kind of various, if you want. This is something that you want to be around your context and to protect it from other non-good citizen talking about your business, right? So the legacy, for example, for us is that kind of not good citizen because it has specific representation and they don't play well with our new model. But now we need to agree on the shape of the data that flows through those contexts, right? And this is where published language is super useful. So published language is about defining a schema, a set of schemas. And in our case, this is Avro. So we use Avro schemas. And each schema is kind of a shared contract between the supplier and the consumer. We have a few hundreds of the schema, and they live on GitHub. So if you want to change the schema, you have to do a pull request. And usually when you are a customer, you are very keen on seeing what kind of changes are done on the schemas that you are using, right? The change is usually driven by the supplier, because you don't want to end up in a situation where you craft specific schemas for different consumers, right? So we try to publish what our context knows about the business so far, and this is made available, and then consumers can come and consume from that and derive new kind of information or just select a subset of that information. So let's have a closer look at one of the boxes. So the loan manager, which lives in the loan servicing context. It's made of 2 microservices. So the first one is called Muxer, and the second one is called Core. So Core as in functional core, which is another concept in domain-driven design where your business logic lives. So So now, how do we apply the correct change given an event that comes in and a given loan state, and make sure that we don't end up in a bogus state? So the loan manager's job is to take an event. For this example, it's a repayment released. And then it has a loan store where it stores what it knows about the loan so far. It checks, the box just checks if it can apply the repayment released event. If so, it applies it. And finally, it updates the loan store with the newest state. And then it publishes the new state, okay, for the outer world to know about it. And also the repayments it emitted along the way to react to that event, okay? So if a repayment has been released, once it's been applied by the loan manager says, hey, repayment paid, right? And we have a few more of these events. So we can also receive repayment reversed. And in this case, we have to react and say, hey, reversal applied, default requested. If, for example, the loan hasn't been repaid for quite a while by the customer. And then we say, hey, loan defaulted. So to control that change, we use the aggregate. The aggregate holds related objects, and they are tied together by the root entity. So in our case, that's the loan. And for example, it will make a lot of checks to make sure that we don't end up in a bogus state. We have 15 different checks, and we have 12 events to react upon. So we need to obviously kind of associate some checks to various events. It's not all the same. Example of checks is, for example, check repayment does not overpay. If the loan has been fully paid, we can't accept a new repayment, right? Because we would be taking more money that the borrower has taken initially, right? Check reversal has an existing counterpart because we can't reverse a payment which we haven't ever seen in the first place. Or check reversal is flagged correctly. So it has to be authorized and reconciled and released. So now there is a question that is super important to us is how did we end up in that state and what happened? And this is what event sourcing is about. A quick show of hands, who knows about event sourcing? Good, okay, nice. So event sourcing allows you to keep track of what happened in the aggregate. So we start with an empty state. We have a loan originated event that we emitted at the loan manager level, which is, for example, yeah, we lent 100. And so we apply that to the, so the red arrow is the apply function, right? It's just a Clojure function. We apply that to the empty state. So, and we say the current loan balance is, the current loan state is remaining 100, and the status of the loan is live. And then we have repayments every month. So repayment paid 10, remaining decreases, that's 90, live, etc., etc. And if there is a repayment of 80 at the end, because I already paid 20, that means it's paid completely, right? And so we transition to remaining 0, and status is prepaid. So let's have a look at what event sourcing looks like in Clojure and Kafka Streams. And so we have implemented the aggregate using a def record, which actually holds the loan state. And it implements this protocol above, the loan aggregate protocol. 2 functions, handle a command and get state. So handle a command is actually, so takes the aggregate, obviously, and takes an event plus a list of coeffects. So coeffect as in reframe, if you use and know the framework. So it's in order to try to push the side effects out of the aggregate and the processing function of the aggregate. And the second one is actually, there is a built-in functionality in Kafka Streams, which is called the state store, which allows you to have state, basically, that you can update with a particular function that you pass to the Kafka Stream framework. And this function actually has this signature. So you pass it the state, and you pass it a Kafka Stream record. So in our case, the record is just the loan ID and the event that we want to react upon. And so the whole function is just those 3 lines, right? So create the aggregate from the loan state. The loan state has been pulled out of the state store by Kafka Streams. And then we call handle command on that aggregate, given the input event that we want to process, and some side effects that we want to get out of the core function. And then we return the new state of the aggregate, and that's it. So React2 is the function that will apply, that will actually do the event sourcing. So we have this event function, this emit function. We create a new event reacting to the input event. We associate the data that we had previously about the side effects, for example, a new ID and what was the parent ID. So parent ID is not really a side effect, okay, because the ID is passed, okay, in the event. And so we take the loan state, we apply the new event. So that could be, for example, decreasing the balance. This is one kind of application. Apply event is a multi-method. And then we append the event. So the state actually looks like very much what we know so far about the loan and the list of the events that we had and that we reacted upon. Sorry, that we emitted to end up in that state. And that's how we did event sourcing. OK, there is one last DDD pattern that I'd like to show you. It's the hexagonal architecture. Who has heard about hexagonal architecture? Quite a few hands. Cool. So hexagonal architecture is about separating the domain logic from the infrastructure concerns. So try to think about like an HTTP request that you want to deal with, or in our case, a Kafka Stream record, and you would like to translate that into an application event. So you don't want your nice functional core to have to deal with HTTP requests or Kafka whatsoever. So hexagonal architecture will help you divide that in clean, separate layers. So the domain is in the inside, and the infrastructure layer is at the outside. And the infrastructure only communicates via the ports. So these are the little semicircles in gray. And in the infra layer, these are the adapters. So how we built our hexagons. So we started with pure domain logic, pure data, Clojure data structures, and also a finite state machine to begin with, to handle the commands with just a pure function, which made it super easy to test, actually. And we, very early on, we added like example-based tests using BDD to test those. And our BDD runs in 300 milliseconds, actually, for 40 tests, which is kind of OK. Also, we added, obviously, many generative tests also on top of that to make sure we never end up in a bogus state. We then added a topology so Kafka Stream topology, to read from the events on the input topic and to pass them to the loan aggregate, which is a protocol, by the way. So that's a good fit for a port in the hexagonal architecture. And then we connected that topology also to the loan store, as I showed you with the aggregate function. And so obviously there is no side effects within the domain, and all the side effects are in the infrastructure layer. And then we just had to add a few more topologies to produce what in Kafka Streams we call a changelog, which is kind of a mutating representation of a state. And also regular topics, which have events in it. So repayment paid, for example, and repayment reverse. So we ended up like having maybe, I think it's 12 topics at the input, and probably 10 at the output. I don't remember exactly the numbers. So this is what our module dependency looks like. So we have this core microservice and Muxer microservice, and they are tied together by a system module, which deals with everything related to configuration, that kind of stuff. And in the infra layer, you can see that we just have dependencies on Kafka Streams and stored service component. In the domain, we don't have that. We just have dependency on CLG UID, which is a third-party library, and we only use the deterministic function. And yeah, camel steak kebab, right? So, in conclusion, I think it's a good move to learn domain-driven design. There is a lot of useful stuff in there. The bounded context separates the domains. Publish language binds the context with contracts. Aggregate controls the change, and event sourcing keeps the history. Hexagonal architecture is about separation of concerns. Remember that these DDD patterns, they solve specific problems, so try to not turn that into a kind of pattern frenzy, okay? Just don't apply them blindly. Thank you.